Hi students, now let us discuss about angular harmonic oscillation or angular harmonic motion. Now in the previous videos we have studied what is meant by linear simple harmonic motion. Simple harmonic motion may be either linear or angular. Okay. Now first in linear harmonic motion what we studied I will recall. In linear SHM, okay, in linear SHM, we studied that the force is directly proportional to the linear displacement. Is it not? But in angular SHM, what we are going to study is instead of force, we are going to consider the term torque. So the torque is directly proportional to the angular displacement. This is the only difference. Okay. Now, for example, let us take an object which is suspended from a rigid support like this, okay, vertically. Now, this wooden block is going to be rotated in the anti-clockwise direction. See here, 90 degree, I have rotated this wooden block and I am leaving it. Does it come back now? Yes, it is coming back. It is turning back in the clockwise direction. Again, does it go back in the anti-clockwise direction? Yes. Slowly the angular displacement is decreasing and finally it is coming to rest. Whenever the object is coming back to rest, the resting position only is called as the mean position. In a similar way, if you take a bar magnet and suspend it, it will rest in the north-south direction. If you rotate it through a small angle and release it means it will also undergo like this wooden block. That is, clockwise and anti-clockwise rotations will be alternately taking place. Such oscillations are only called as what? Angular harmonic oscillation. Okay. Now, in the picture I have shown a circular plate, a circular disc, which is held in the horizontal plane, and it is suspended by a small string from a vertical stand. Now, this is rotated in the anti-clockwise direction first and released. Then after some time now it will oscillate back in the clockwise direction, again anti-clock, then clockwise, and finally it will come to zero. When it will come to zero, when the net torque acting on the system is equal to zero. So the position where the net torque acting on the system is zero, no, that is denoted by O. This is called the mean position. So with respect to the mean position, the circular displacement is turning clockwise and anti-clockwise. So whenever the circular disc is rotating in the anti-clockwise direction like this, it produces a small displacement theta. Can you see here theta? So at one extreme position, on the right extreme position, this theta will be maximum. So that is taken as positive maximum theta. That is, theta will be positive maximum when it rotates in the anti-clockwise direction. Again it rebounds, it crosses the mean position and it rotates along the clockwise direction, and here also it reaches a maximum angular displacement, that is denoted by what? Minus theta maximum. Then slowly, due to air resistance and the damping forces at the suspension point, it will come back to the rest. So here the oscillations of this circular disc is said to be simple harmonic. Okay, it is said to be simple harmonic. What is the name? What is the name of this circular disc? This only is called as a torsional pendulum. Okay, this can be called as a torsional pendulum. We have studied simple pendulum, is it not? We have studied simple pendulum. So in the same way here, now it is called as torsional pendulum. Some other examples I told you. The bar magnet freely suspended, when it is twisted means it will also undergo angular SHM. Okay, in addition to that, the balance wheel inside the old type of watches, wrist watches. Okay, these are all examples for what? Angular SHM. Now, we want to derive an expression for the period of oscillation of angular SHM and the frequency of oscillation. So for that, let us go by the definition of SHM. So in angular SHM, the torque, okay, torque tau, the magnitude of the torque tau is proportional to the magnitude of the angular displacement, or torque tau is equal to minus k into theta. So this I will consider it as the first equation. So similar equation we have studied force, linear motion. In linear motion, force is equal to what? F is equal to minus k times x or minus k times y for linear motion. Okay. Now, from the definition of torque, okay, from the definition of torque, we also know that torque tau is equal to I into alpha. What is here I mean? I is moment of inertia of the rigid body. From the Newton's second law, force is equal to what? Mass into acceleration, isn't it? So, the role of mass is played in rotational motion by moment of inertia. Similarly, instead of linear acceleration, I have substituted alpha, which is called as angular acceleration. This is nothing but Newton's second law in rotational motion. Okay, so I am considering this as equation 2. Now I am going to equate these two. So from 1 and 2, I alpha is equal to minus k times theta, or alpha is equal to minus k by I into theta. Okay. So the angular acceleration alpha is equal to minus k by I into theta. So this is equation 3. In this equation, now k is called as a torque constant. In linear SHM, we have studied force constant. Force constant means in linear motion, k is equal to what? Force divided by displacement, F by x or F by y. Here it is a tau by theta. So this is k is equal to what? Torque required to produce a unit displacement. So torque per unit angular displacement, and hence its unit is Newton meter for torque, and denominator there is a radian. So it is radian power minus 1. So Newton meter per radian is the unit for the torque constant. So this concept, I think you must have studied this concept in moving coil galvanometer, suspension coil galvanometer. That is again a best example. Understand? For the angular SHM. Okay. So this is now equation 3 to be highlighted. Now what is actually angular acceleration is equal to? Angular acceleration is equal to d omega by dt, rate of change of angular velocity omega, which is the second derivative d square by dt square, second derivative of the angular displacement. So in place of alpha, I can also write therefore d square theta by dt square. It is nothing but alpha. Okay, the other term instead of alpha, d square theta by dt square. So this is equal to minus k divided by I into theta. So this is rewriting of equation 3 only. Equation 3 only is rewritten in another form. Let it be as it is. Now from the definition of SHM, angular SHM. So this angular acceleration is d square theta by dt square. This also equal to what? Omega square into theta with a negative sign. Okay, omega square into theta. So I can write this as minus omega square into theta. What is the similar equation in linear SHM? We wrote instead of this theta, d square x by dt square, or d square y by dt square is equal to minus omega square times x or y we wrote. So here it is replaced by theta. Now you can look at the left hand sides of equation 3 and 4. They are equal. So I am equating equating 3 and 4. The right hand sides. Okay, equating the right hand sides of equation 3 and 4. minus omega square into theta is equal to minus k by I into theta. So the negative sign gets cancelled and theta gets cancelled. What remains is what? Omega square. Okay, so omega square is equal to k by I. Okay, or omega is now equal to square root of k by I. Okay, this is one very important information for us. Therefore, period of oscillation, okay, period of oscillation is represented by the symbol capital T, that is equal to what? 2 pi by omega. So this is now equal to 2 pi divided by square root of k by I, or you shift this to the numerator. So T will be now equal to 2 pi into square root of I by k. So this will be equation number 5. Do you remember? For linear SHM, we derived this equation as what? T equal to 2 pi into square root of mass divided by k, m by k. So inertial factor divided by spring factor. So here instead of mass, there is a moment of inertia. Understand? Because the rotational analog of mass is what? Moment of inertia. Okay, if you take reciprocal of this time period, what do we get? Yes, that is frequency. So the frequency of oscillation is given by F equal to 1 by T, and this is now equal to 1 by 2 pi into square root of k by I. So all these equations are similar to that of linear SHM only. Is it not? So first we started with the definition of SHM. So according to definition of SHM, we have studied that the force is directly proportional to linear displacement. Similarly here, the torque is directly proportional to the angular displacement. That is the beginning step. So torque tau is proportional to theta, or torque is equal to minus k theta. Then from Newton's second law of motion, force is equal to mass into acceleration in linear motion. Like that in angular motion, in place of force, torque. Torque is the product of moment of inertia I and angular acceleration alpha. So then we got an expression for alpha, and comparing this with the definition of SHM, once again another equation for alpha we got. Then we have derived this equation. I hope you must have understood well. Fine.